Have that.
Good. All right. Thanks, Franklin. And yeah, just while we're waiting, I'll just fill in a little background. I see Michael has a question about the Meerkat telescope. I'm not sure what the Meerkat telescope is. Let me look. Yeah, see, Meerkat's a ground-based telescope in South Africa, and yeah, Michael, this is different from Meerkat in that it's in space, and not only is it in space, but it's 1,000,000 miles away from Earth, as we'll talk about here in my slides. So it's seeing the universe without any of the the cloudiness or obstructions that you get from our atmosphere, and that just opens up a whole, wide array of things that you can see. So yeah, it's been a really exciting week for Webb and for NASA, and I'm excited to share some of that information and give you some background. We'll give it a couple more minutes for people to join. And
I thought I'd do my intro and then I'll hand it over to you because that should roll us into the hour. So I'm Franklin Escobedo. I'm the Community Services Director here at the Larkspur Library, Larkspur Recreation. And we're really excited to have Ron Rosano back. He's our solar system ambassador from NASA, who has been coming over the last few years to give us different talks on different parts of NASA's different programs. And then one of the big ones that I think we mentioned is when we did the one on the space race, of the new space race, we talked about the telescope. And so it launched, and then it's in space, and then it deployed, and then just this week, on Ron's birthday, we got some really great presents, and that was the first images from the Webb telescope were released to the public. And so we're here today with Ron Rosano, who's gonna talk to us and show us all the different and exciting stuff that's going on. And then I'm gonna be hiding in the background, Ron, so if you need me, just ping me, I'll turn my camera and mic back on, so.
Great.
Thanks.
Thanks, Franklin. And will you keep an eye on questions and things as they come into the chat?
Yes, and then I'll relay them at the end. So.
Great, thanks. So hey, everyone. My name is Ron Rosano. I'm here at home in Muir Beach. I'm a lifelong Marin resident, and great to have you all with us. And I'm really excited to talk the amazing science that's come out of it. Mentioned Tuesday was my birthday, and we got a really wonderful gift from NASA. I got a wonderful gift from NASA with the release.
Well, you're getting choppy on my side, Ron. It's weird.
Let's see. I'm not sure if I have. Oh yeah, I've got a. You sent a message that said my internet was a little unstable. I'm not sure what I could do to fix that.
Okay.
Let me try one thing here. So yeah, NASA released some the first introductory images from the Webb telescope, and let me go ahead and share my screen and give you a little background first on the Webb telescope and a little history of it and the construction of it, and then we'll get into those first images. Is that coming across okay? There, Franklin, you can see it.
Yes, it's coming across.
So yeah, Christmas last year, maybe some of you might remember, NASA gave us a great Christmas gift and launched the Webb telescope into space. And it's been about a month on its way out to its location in space, where it's going to stay. And tonight we're going to go through five components, really just a little background, talk about the elements of the telescope, some of the innovations that it's doing, take a look at the first images, and then have some Q&A. So who's James Webb? Well, he was the NASA administrator in the Kennedy and Johnson administrations, and oversaw NASA's great success landing men on the moon during the Apollo era. So as a credit to those contributions, the telescope was named after him. And the telescope was started about the initial designs and thinking really date back to 15 or 20 years. And with these four main goals is looking deeper into the universe, the early universe, and examining how the universe was formed and how galaxies evolved over time. And then they're also looking closer in within the Milky Way galaxy at life cycles of stars and looking for exoplanets, planets that are around other stars. So here's an image that represents the timeline or the scale of how deep back into the universe the Webb telescope can see. There's the Big Bang way over on the right, and you can see in the pink line that the Webb telescope is looking back to about 200 million years after the Big Bang. So common understanding now is the universe began with the Big Bang 13.8 billion years ago. But the Webb telescope is going to be able to see about 13.6 billion years ago, so way deeper into the early formation of the universe than the Hubble Space Telescope has been able to do. And yeah, one really strange thing about seeing back in time that's a little mind-blowing is that, the nearest stars to Earth are about 4 light years away. So that's the distance that light travels at the speed of light in about 4 years. So when you think about it, what's happening is that the light that we're seeing from those stars left those stars 4 years ago. So when you're looking back into the universe and looking at other stars, you're really looking back in time. So it's an amazing property of this physical world that, because they're so far away, what you're actually seeing is the early formation. You can see into the early formation of the universe. So we'll be studying galaxies and early formation of the universe, and also star formation within our Milky Way. So here's a artist's interpretation of what a star might look like with an exoplanet or a planet that's around it. An exoplanet is really just a planet that's orbiting another star, not in our solar system. So what's amazing about the James Webb Space Telescope really is that they've been so successful in deploying it with this great degree of complexity. There's a primary mirror that's made up of 18 different mirror segments. There's a secondary mirror that takes the light that is focused from those mirror segments and brings it back into a point inside the instrument behind the telescope, where the science instruments can dissect the light and find out more about what the components of that light are. And what's essential about that is keeping the telescope cool, like hundreds of degrees below zero, and shielded from the sun. So they built the system of sun shields that keep the mirror out of the sun for its entire life, and protect it from the heat of the sun so that the instruments can operate at their very cold temperatures. I had a visit to NASA Goddard Space Flight Center in Maryland in 2016, and shot this photo and the next couple of photos, and it was astonishing to me to see the size and complexity of the telescope. And it just seemed to me audacious that they're spending billions of dollars to build such a complex instrument. And then not only are they building it, but they need to launch it into space And it's also not in near Earth or in Earth orbit at all. It's stationed 1,000,000 miles away from Earth, so that it's not bothered or interfered with by the light and energy from Earth, and it can take observations in a quiet space. So to think about that complex of an instrument being so far away and putting it all together was just amazing to me. So there's a close-up of two of the technicians with the secondary mirror. That mirror is about 2 feet in diameter. And here's another photo after those technicians were lowered down closer to the primary mirror. And what's fun to notice here is you can see the curvature of the mirror shapes there that gather the light as it comes in from far away and reflects it back to the secondary mirror. And also you can see the reflectivity of the mirror segments. They're actually they're mirrors. So there you can see that they're reflecting objects like the ladders and structure behind them. So here's a depiction of how that light reaches the instruments. It's how the telescope works really is it's gathering light, like our eyes, but in an enormous size, and gathering light over a large surface area and bending light with mirrors and focusing it down into the scientific instruments so they could have a much brighter amount of light than they could get with a smaller mirror. And that's really the breakthrough of the Webb telescope, is it's much larger than the Hubble Space Telescope. So here's a little close-up of the primary mirror and the primary mirror segments. At the bottom left there is one of the mirror segments, so you can get a sense of idea of how large it is compared to a person. And what's also really interesting about those mirrors, every one of the mirror segments has 5 motors attached to it, so that the motors can push and pull on parts of that mirror segment to bend it ever so slightly, so that the entire surface of the primary mirror is very precise in the way it's pointing the light. So it's a very complex design. Here's an image of the backplane that holds the mirrors and the sun shield. The sun shield is made up of 5 layers of super thin mylar material, and they are altogether, the sun shield is about as big as a tennis court. Here's some of the instruments. Here are the 4 instruments that are contained behind the mirror. So this is all the work is being done. They are detecting light in the infrared part of the universe, in the infrared part of the spectrum, a little bit different from what our eye sees in the visible part. But they need to do that in order to look back farther in time. So in order for them to be most effective, they need to operate at extremely cold temperatures, minus 300, minus 350 degrees Fahrenheit. And one of the big breakthroughs that we see with the Webb Space Telescope is that it's using micro shutters. So it's using tiny array of shutters to direct light into different parts of the different instruments, so that while the telescope can be pointed in one little part of the sky, one instrument can observe this part of the view, another instrument can pick off that part of the view, so they could actually take data from different components within the field of view all at the same time without having to point it at one and then the next. So I found this animation of the path of light. So here's one of the instruments, the mid-infrared instrument, and this is how the light, as it comes from the telescope, is directed down through the instrument into the sensors that dissect the light and get information from the individual components of the light. So this is fascinating to me to see how, what the engineers are using to break up that light and deliver it, in this case, to 4 different sensors within the MIRI instrument, the mid-infrared instrument. So there are these integral field units that do spectroscopy and light, take pictures, grading wheels, and that's just one of the 4 instruments inside. And they just finished a 6-month testing or commissioning of this, and it's operating beyond their specifications. It's been a great success. So here's a few images of the telescope as it was folded up. Because you're launching it on a rocket, you can't you can't launch it in its deployed configuration, so it's folded up like origami. And the secondary mirror is at the top left, that little black portion there, and you can see the primary mirror there in the center, but also there's 3 segments of the primary mirror that are folded back for the launch, and that was part of the deployment sequence, is to bring those side segments out, and there's some people in the bottom for scale. So this is last December in French Guiana at the launch site, putting the nose cone of the rocket around the telescope, and there's the rocket as it sat on the launch pad last December, and then the liftoff on December 25th. Really glad to see that went off with complete success. And then once it was in orbit, as the telescope separated from the rocket, it floated away, and a camera on the rocket caught this picture of the telescope on its way out into space. So where's it going? This is a really interesting part of it, is that in order for the telescope to be most effective, you really want to have it away from Earth and the heat and light and radio waves from Earth that could interfere with the instruments. So it's sent out, took about a month to arrive at what they call the L2. It's the Lagrange point 2. So that's about 1 million miles away from Earth, and it's a point in space where there's a balance of gravity between the Earth's gravity and the sun's gravity. So the telescope can effectively hang out there for its entire life, and as the Earth goes around the sun, the telescope will stay with it. So the telescope can always have a view of Earth and from the sun-facing side, and then the mirror can be opposite the sun, looking at the universe beyond. So here's a little depiction of what how that looks. There are actually 5 Lagrange points in their spacecraft at the L1, L2 points. There's some spacecraft at L1 that are, because they're stable and looking at Earth, they can see the Earth and look at climate cycles and weather continually. This is true of any two-body system. Jupiter has Lagrange points with asteroids ahead of it in its orbit and behind it at L4 to L5. So it's really interesting a condition of, or kind of result of how gravity works with bodies in space. So here's an animation of the deployment. It took about 30 days, had about, I think, over 100 critical points, and had a rocket burn within the first day, deployed antennas. And after about the 3rd day, 4th day, it extended the booms that support the sun shield, and a flap in the back for stabilization. Around before the end of the first week, it started deploying the sun shields. And, again, a very complex series of movements that all had to go perfectly. If any one of the single points of failure had a failure, then we wouldn't have an operating telescope. So about 2 weeks out, they deployed the full primary mirror, and that's the way it looks in its current configuration. Wanted to just touch a little bit on traveling through space and how that works. Because of the forces of gravity and the way gravity works on Earth, you don't travel at a constant speed in space. When the telescope left Earth, it fired a rocket to give it a fine tuning, and about 2 hours later, it was going 10,000 miles an hour. But because Earth's gravity is pulling on it the entire time, just like when you throw a ball up into the air, it's going fast as it leaves your hand and then slows down and comes to a stop and then comes back to Earth. The telescope has those same properties. As it's on its way out from Earth, it's slowing down from gravity, and gravity's pulling on it the whole way. So you can see just half a day after the launch, it's dropped from 10,000 miles an hour to 5,000 miles an hour. And that speed continues to slow as it gets farther and farther away from Earth. And after about 2 weeks, it's only going 940 miles an hour. So it's a very precise calculation to figure out how fast, how much speed you need to give the telescope to get it away from Earth. Here's a graphic depiction of the first month. So you can see it goes from 11,000 miles an hour down to under 1,000 miles an hour in a month. So that's just a consequence of traveling through space. And here's an image that brings that to light a little bit. Good way to think of how things work in space is that bodies are gravity wells. The sun has a lot more mass than the Earth, so it takes a lot of energy to climb out of that gravity well. Same thing with the Earth or the Moon. It's easier to leave the Moon because it's much smaller mass and it's a shallower well. And you can see here also the depiction of the Lagrange points, L1, L2, L3, L4, L5, where the gravity between the two bodies of Earth and Moon, Earth and Sun, balance out to create an environment that's stable, and where a spacecraft can station itself without having to use fuel to maneuver. Let's jump into the first observations. This first one is what's called the deep field, where a telescope looks at a very certain point of space for a long period of time and lets all the light from all those elements in the field of view accumulate into the instruments. And this is a very, very tiny region of space. If you have I have a paper clip here. So this part of space is about the width of a grain of sand at arm's length. So, you can see the little tip of the paper clip here. If you hold that out at arm's length, that little tiny tip is the field of view in this image, which is just amazing to me. So you could take this picture in almost any part of the sky and have this same result and see all the things we're seeing here. And a lot of those, most all of those are galaxies. And what's fascinating about this is that they chose this region because there are actually galaxies in the foreground of this image and other galaxies in the background. So you're looking past some near galaxies and seeing some galaxies behind it. And what's happening is that the galaxies that are closer to us are bending the light from the other galaxies. And you can see that in the strange shapes, the lines that you see, the kind of vertical lines, and just to right above center, there's a kind of a globular looking galaxy. That's a normal galaxy, but because of the gravity in the galaxies in front of that, the light from that galaxy is bent. And this was actually something that was theorized by Einstein. And he actually said that, oh yes, gravity should be able to bend light. And it wasn't until later that scientists were able to do the experiments to prove that was correct. And you can see it's very obvious in this image. Here's a comparison of Hubble Space Telescope image versus the Webb image that just came down during the commissioning period. Same region of the sky, and interesting to note that the Hubble Space Telescope took weeks to gather enough light to create this image, and the Webb Space Telescope took about half a day to gather the amount of light to produce this image in much greater detail. So this is really exciting for scientists that not only can they see farther back in time, but they can also get data much quicker than they have been able to before. This is one of the other images that NASA released, and it's actually not a visible image of the object. It's a spectrum from a planet that's orbiting another star in our galaxy. And the planet is passing in front of the star in what they call a transit, kind of like an eclipse. So when a planet that's orbiting another star passes in front of the star, we can see that the light that we get from the star is diminished, and it's not, the star is slightly less bright. And they've seen now in the last 15 years, thousands of planets around other stars using this method and saying, well, wait a minute, if we're sharp enough to detect little changes in light, the amount of light from a star, then it's a planet, and they can observe that repeatedly and say for sure that, okay, that's a planet that's orbiting, and we can determine the orbital period. And one other thing they can determine is what are the components in the atmosphere of that planet. So by using the instruments on James Webb and waiting and watching for a planet to transit and go across the front of a star, they can detect the components of the elements in the star's atmosphere, and then use their spectroscopy to determine that yes, there's actually water in the atmosphere of this planet. So that's one of the main focuses of the James Webb Space Telescope, is that'll be looking at other planets around other stars and helping determine what's made up in the atmospheres of those stars, and hopefully find more planets with water and other life supporting kinds of elements. This is the third image. This is a planetary nebula in the southern hemisphere. It's known as the Southern Ring Nebula because we have a ring nebula in the northern hemisphere that's a little better known. So this is called the Southern Ring Nebula. And these are two images from two different Webb instruments. One in the near infrared light and one in the mid infrared light, two slightly different wave bands. And you can see each of those frequencies of light will show different components of the star. And one thing that was really exciting to see here is that if you're looking at it at the nebula in the mid-infrared light and the image on the right, you can very clearly see that there's not one star in the middle, but there's two. So this is a binary system. These are two stars that are gravitationally bound that are orbiting each other, going around. And that's part of the reason, because the effects of their gravity changing, that the star, which exploded in the middle to cause this shell, is coming off in like concussion waves. I'm going to dive a little deeper into that. Here's a Hubble image versus a Webb image. And you can see, even though the Hubble image is fantastic and shows beautiful colors and structure, the Webb image is really a step much farther beyond. And you can see the layers in the outer rings. And scientists are like tremendously excited to look at this. And NASA's making all these images public and available to scientists. All the data is available to scientists, so astronomers from all over the world can look at this data and start to draw conclusions, make proposals for the next round of observing. Excuse me. Here's a close-up of one of the regions there, and you can see that the Webb images, because of the wavelength that's operating, is actually showing stars on the other side of the nebula that you didn't see in the Hubble image. So it's just a really exciting time for astronomy and science. The other focus of the Webb was to look at galaxies and understand galaxy formation. So this is a group of 5 galaxies called Stephan's Quintet. This is a combined image from 2 of the instruments on the Webb. So they're actually 4 of these galaxies are gravitationally bound and in the same region of space. Those are the 4 on the right-hand side. The one on the left is actually much closer. It's about 20 million, 24 million light years. Let me make sure I have the right number there. Yes, it's about 24 million light years away. The nearest one, and the other 4 are about 290 million light years away. So although 40 million and 290. So even though they look like they're kind of in the same place, they're actually, one's close to us and 4 are farther away. So what's fascinating about what's happening here is that the 4 that are farther away, you're seeing disturbances as they're moving through space, and the gravity of the stars within the galaxies are affecting each other and causing these dynamic shapes and things. My friend John Dobson would call this galaxies playing contact sports. As a bonus here, like the deep field image, the Webb telescope is revealing thousands of distant galaxies in the background, far beyond these other galaxies that are about 290 million light years away. You also notice some star points in there. There's some 6-pointed star images near the upper right. Those are stars within our galaxy that are also just in the same direction that we're looking. They get those diffraction lines due to the shape of the telescope. Because it's a hexagonal shaped telescope, you get the 6 lines like that from stars if you're doing these kinds of observations. Here's a close-up of 4 of the galaxies, 3 of the distant galaxies, and then the one that's closer up. So really amazing amount of detail. I mean, every one of those galaxies could be studied and categorized, and this is just a groundbreaking moment for astronomy and space science. The 5th and the last image I'll talk about before we get to Q&A is the star forming region in the Carina Nebula. The nebula is it's like we saw in the earlier image. It's gas and dust that's blown away from stars. This is an image by the near infrared light. And I'll start with this image. This is from an Earth-based observatory in Chile. This is a larger view of the nebula, and you see down below center there's a little nodule. And I've taken a little zoom in on that nodule in the upper left image, and we're going to have a look at that with Hubble and Webb in a minute. But you can see even with the ground-based observatory, it's like a spectacular image with, you know, all kinds of things to look at. But what you really want to do in astronomy is put a telescope in space. And here's a comparison of that same little nodule with a Hubble Space Telescope image on the left and a Webb image on the right. And you can see, wow, yeah, the Hubble telescope is a spectacular image and really beautiful. And the Webb, you know, to me, takes it even farther. And these are stellar nurseries. And if you were looking at this in visible light, the light, you know, with our eyes, we wouldn't be able to see it. But because Webb is sensitive to infrared light, you can see through the dust that obscures the visible light and see details in the object that wouldn't be there otherwise. So, you know, what they're looking to learn from this is, you know, the processes of star formations, star formation, how do stars form in a certain region, you know, how do they develop out of, you know, the components of gas and dust that make them up. So that's here's a little summary of, you know, the 4 areas that Webb is focusing on. It's going to be a very exciting time. And one of the amazing things is these are not its best images. These are, okay, they're trying little things out with the telescope. Now that they know that it's working beyond specifications, and they can devise other observations that bring it even more in depth. So it's just been a great week for NASA and for Webb and for scientists all over the world. You know, this is not just NASA in the US building this. It's the Canadian Space Agency, the European Space Agency, and really glad to have. I'm really glad to see, you know, all that cooperation. So ready to go on with Q&A.
So the first one was someone asked if you could do a comparison that gives perspective for 1,000,000 miles.
Oh, like for 1,000,000 miles, like if we were going to look, if we were 1,000,000 miles from Earth looking back at the planet, let's think. You'd probably see some, well, for one, Webb is not going to look at the Earth or any of the planets because it's too close to the sun. It could burn it. It could damage the telescope. It will look at the outer planets, you know, like Jupiter, Saturn, Uranus, and Neptune. But what would Earth look like from 1,000,000 miles? You'd probably see a point of, you know, you'd probably see it in a disc kind of shape or a ball kind of shape with some detail in it, especially if you have binoculars or a telescope. So on the moon, you know, if you think of the moon and the Earth sky, if you were to flip that around, the Earth is 4 times the diameter of the moon. So if the moon is this wide, then one finger wide, and the Earth is 4 fingers wide. So if you were on the moon surface, the Earth would be 4 times as large as the moon is in our sky. So yeah, very different views.
Okay, so the next one was what causes the distortion in the center of the SMACS 0723 image?
Thank you. Yeah, the distortion is like I was getting at a little bit. It's galaxies between the galaxies that are farther away. So there's galaxies that are closer to Earth, and then they're looking at galaxies farther away. So it's kind of like the gravity from those galaxies is taking like what would be like a nice round galaxy image and bending it as it comes around, and it looks to us like a little sliver instead of a nice round galaxy. So it's gravitational bending that's changing those.
Now, two questions happen at the same time. So if the image is rendered non-visible light as visible by using color filters, would we see almost nothing if the images were showing us visible light only?
Yes, if you were looking at, if you're looking, you know, at that, if you have a telescope, if that telescope was pointed at those objects, if Webb was looking at visible light, the clouds of dust would obscure it, and you wouldn't see anywhere near the amount of detail that you get. But by looking at infrared light at different wavelength, the infrared light is able to pierce through those dust clouds, and you know, kind of make them go away, make them invisible, so that you can see the objects behind it.
The second part of that question was also the choice of filter colors partly is an artistic choice.
Oh, good question. Not so much. I think there's, my guess is the scientists let the artistry of the images kind of come out from the objects, and the filters really are more based on wavelengths. You know, if you look at the electromagnetic spectrum going from, you know, radio light that's long, and then X-rays on the other side that are short. The telescope has like what they use these filter wheels. So like a circle with all these little filters in around the edge, and they turn the wheel so that the light goes through, you know, the different filters and like picks off certain wavelengths of that light. So
the last question we have so far is, so with the nebula pictures, do the varying colors indicate intervals of temperatures?
Do they indicate intervals of temperatures? I'm not sure, but I would think so. I think there's temperature difference between, you know, the different parts of, you know, the material that they're seeing. So I think that's I would guess it's a component of it, but I'm not a scientist, so I can't quite say for sure.
So are there any more questions? You could use the Q&A or the chat box. So
yeah, I'm happy to have any anything you'd like to ask in the chat. Let's see. I see one from Katrina about our binary stars.
oh, yeah, that's right. I missed that one.
Yeah. Are binary stars more common in our universe, or singular star systems like our own? Yeah, that's actually something that's come out of astronomy in the last, you know, 50, 100 years or so, is that they're finding that just within the Milky Way galaxy, which we know pretty well because those stars are much, much closer. It's way harder to see individual stars in other galaxies. So within the Milky Way, binary stars are surprisingly common, as many as half. I think star systems could be binary, and there's even triple binary stars where there might actually three stars is harder to have, but you can't have two pairs of binary star systems in a stable configuration where you'd actually have four stars that are gravitationally bound and going around each other. I see Michael's question about totally random, but why the launch from Guyana? Yeah, great question. That's actually, there's some interesting parts of that. It's always good to launch rockets close to the equator when you can. That's partly why, that's a big reason why Kennedy Space Center is in Florida and not in New York or somewhere. They want it by the ocean, so if something goes wrong with a rocket, it falls in the ocean and not on people. Also, the Earth is about 24,000 miles in diameter. So in 24 hours, it's spinning 1,000 miles an hour at the equator. So as the Earth is spinning, you want to launch a rocket in the direction of the spin to take advantage of that acceleration, that natural acceleration, you know, that you get from the planet. If you're farther north, you're maybe 500 miles an hour of acceleration. So being next to the ocean and being near the equator is where you want to be for rocket launches.
And then, how does the JWST expand our understanding of science, space-time, or maybe confirm that idea?
Space-time, yeah, that's a difficult. I haven't heard any of the scientists or NASA talking about that astrophysics kind of understanding of a space-time and like particles and things. It's their focus has been more on, you know, galaxies and, you know, the four things that I highlighted there. So I'm not sure if that's, I know I'm not really great at theoretical physics, like understanding space-time. So
A few more years, they'll have this all right.
I'm not sure about that one. But thanks for that.
Okay, is there a plan for the next telescopes in the works?
Oh, I'm not sure. You know, scientists do what they call a decadal survey every 10 years. They get together and say, okay, here's our priorities. And the Webb telescope was a product of that and said, yeah, we should take the Hubble Space Telescope and make a giant leap with that. What they don't want to do is, you know, just improve it a little bit. It's really worth it to make the effort to make it way better. So that's what Webb was compared to Hubble. It's about 100 times the resolution. It's like 2 orders of magnitude better at gathering light and analyzing light. And I don't know if there's a bigger telescope or you know, any plans for a way to make that next leap. But it's something that's, you know, probably in process now in a kind of a more basic plan.
I like the next one because I have the same question. How do scientists protect the telescope from being hit by other objects?
They can't really. They're at the mercy of, you know, debris that's out there. But that's one advantage of being out at L2 rather than in Earth orbit, is because it's much cleaner area out there. That is part of the design of Webb, is to they expect it to get hit by micrometeoroids. In fact, it was in the news a couple of months ago. The telescope was hit by a micrometeoroid, a piece of gas or a piece of dust or speck of something that was actually bigger than what they thought might be their average size. But it really hasn't affected performance in any large way. And that's one of the advantages of having every one of those mirrors having the ability to be shaped and bent so that the surface can adjust itself to align perfectly with the rest of the mirrors. So also, yeah, I think that's a trade-off really between where you point it and what the risk is. Of course, if the telescope's traveling through space in one direction and the sun shields facing in the direction of travel, you're going to get, you know, hits on the sun shield, but the mirror won't get any. But because the telescope travels more in a kind of inline path, so if the Earth's here, this telescope's going around it, and the telescope's always pointing at different parts of the sky, and it's traveling more like head to toe across it. So it's not traveling with the mirror like full on in the direction of travel. So.
Okay, so the next one is, what have you learned on a quick look so far that you didn't know before?
Wow, that's a great question. Let's see, it's still early. You know, it's been a couple of days. So I was listening to the media press conference from Webb, and yeah, fantastically that the telescope is operating exactly as they designed it and actually beyond. And another good thing that happened is that the precision of the launch rocket was so good that they're going to have to use less fuel from the telescope itself. So they actually were aiming for a 10-year lifetime, but they'll have enough fuel to run for 20 years, which is great. One of the reporters that was asking the scientists in the media briefing, what do you expect to get? And the answer from the scientists was you can't guess what the most exceptional thing is going to be. And the example was the Hubble Space Telescope. One of the objectives of it was to get a precise estimate of the Hubble constant, which was the expansion rate of the universe, which they were able to do. But what they didn't expect from Hubble was that after more science years later, they were able to determine that the universe is actually expanding at a rate that they didn't realize. And that was a Nobel Prize. So the things that they get, that's like part of the excitement of it, is what you can't predict what's going to come out of it. You put all the world scientists or astronomers on this data, and you could come up with some extraordinary things. But one thing in particular is like the early formation of the universe and how galaxies got together. That's something that's never really been able to be studied before.
The question, I'm not sure about that. What are the things that look like land? That was the question that Spencer asked.
Oh, I guess maybe one of the images had things that look like land. I'm not sure whether that was been like the Planetary nebula image, maybe, or something else. If you're thinking of the Planetary nebula, Spencer, and even if you're thinking of like the Carina Nebula, that would be dust, gas and dust, mostly, that's lit up by the stars in that region. And if you want to elaborate more on that, feel free.
And then another one is, you mentioned that the telescope would be used to photograph the planets. Where can we expect those images to be released?
Oh, they were saying yesterday that they've taken the pictures of Jupiter. So boy, the next week or two maybe. They didn't say. They do have pictures, I think they said, of Jupiter that have been taken during this 6-month commissioning period, and they're releasing to the world 40 terabytes of data today. Yeah, so like an enormous amount of data that they're sharing, and I just think it's great that they're making that available for anybody that wants to look at.
So, so the last one, can you explain a bit more about the 6-point effect of do they have this one, a 6-point effect in telescopes? How does that fit into the old paintings of 6-pointed stars?
Oh, yeah, maybe. The 6-pointed stars, I'm not sure, or 5-pointed stars if they came from telescopes, but this is in particular, there's actually even some other artifacts in there. Those are artifacts from the shape of the telescope. So if it was a round telescope and wasn't broken up into all those mirror segments, you wouldn't have those. But there's also some smaller rays that are caused by the structure that holds the secondary mirror. There are 3 support arms that hold the secondary mirror out, and when the light comes in from the stars, it's actually passing through those. So those 3 support bars or beams actually cause 3 other of these diffraction lines, or not diffraction lines, but these star lines. But when they were engineering the telescope, they actually designed it so that the lines that result from 2 of those bars line up with the line, the 2 of the 6 lines that come from the shape of the telescope. So it's a little less messy than it would be if they didn't do that.
That was the last question, it looks like. So
Cool. Thanks, everyone. It's been great sharing the excitement. I thought it was great that the president came out on Monday night and revealed one of these 5 images, and that's it's great to have this in the news and great to have astronomy sharing all these interesting things about our universe. I think it's really important for us to have an awareness that we're all on this planet together, in this we're all crew on this planet Earth, and it's really imperative for us to be aware of that and to work as best we can to keep the planet in as best shape as possible. So
thank you, Ron. And I guess that was the best birthday present, was to get these images released, and we can't wait till you come back. And
those folks at NASA are the best.
But yeah, we can't wait till the next time you come and visit us and share us more excitement about space and our space program. So
I will. And just to, as a preview, keep an eye on the Larkspur Library information if you're interested. I'm glad to say that I've had the opportunity to fly into space with Blue Origin. I can't say when, but I expect to be working with Franklin and Teresa at Larkspur and doing a little presentation about what it's like to actually fly into space sometime in the not too distant future. So
keep an eye out, but we wish you luck and we can't wait to see you back. So
well, thanks so much, and thanks everybody for coming.
And thank you, everybody. Have a good evening.
Okay.
Bye.